Welcome, curious minds, to another deep dive. Have you ever wondered how physicists tackle problems that seem, well, just completely impossible?
Problems that give answers like infinity.
Exactly. Today, we're diving into the remarkable story of how scientists grappled with one of the most frustrating, um, really fundamental challenges in quantum theory, a challenge that seemed to break logic.
That's right. We're going to unpack the journey of quantum electrodynamics, QED for short, largely through the eyes of Nobel laureate Sin-Itiro Tomonaga. His 1965 Nobel lecture, Development of Quantum Electrodynamics, is kind of our map today.
A great map, too. It's a story of, well, amazing breakthroughs, really confusing paradoxes, and then finally this revolutionary fix that changed physics.
Absolutely. It's a fascinating narrative.
So our mission today is to follow that thread, from the early head-scratching to this ingenious solution called renormalization.
Which finally brought those infinite problems back down to Earth, so to speak.
Yeah, you'll hear about different ways of thinking, some unexpected links between theories, and even a critical mistake that nearly stopped everything.
It almost did. So let's get into it.
Okay, so let's set the scene. Our story really kicks off around 1932. That's when Tomonaga, our guide for this deep dive, started his research career. What was the big hurdle right out of the gate, and how did Dirac shake things up?
Well, the core issue, the really big one, was trying to make quantum mechanics play nice with Einstein's theory of relativity. They just didn't seem to fit together easily.
Right, oil and water.
Sort of. The main theory, then, by Heisenberg and Pauli, treated the electromagnetic field itself like a dynamic thing, like particles, something evolving. But then Dirac came along with a completely different philosophy.
And his idea was quite radical, wasn't it? He saw the field differently.
Totally. Dirac suggested the field's role wasn't really to be observed directly like a particle. Instead, its job was simply to allow us to observe the particles.
So like the stage, not the actors.
That's a good way to put it. He felt they shouldn't be on equal footing. And this led him to his many-time theory. See, the old way, Hamiltonian dynamics, it had this flaw from a relativistic view.
What was the flaw?
It treated time and space differently. It used just one time variable for all the particles in a system.
Which doesn't work well with relativity, where time and space are intertwined.
Exactly. Dirac's genius was to give each particle its own time variable, so your probability amplitude, the math thing describing the particle, becomes a function of, say, R1, T1 for particle 1, R2, T2 for particle 2.
And so on. Wow, that elegantly brings time and space together.
Precisely. It respected that relativistic principle. Tomonaga was apparently captivated by this, the novelty of philosophy and beauty of form, he called it.
So he jumped right in. He and his mentor, Nishina, investigated it.
They did, but they quickly found something, well, surprising.
Which was?
Despite all its elegance and different thinking, Dirac's many-time theory turned out to be mathematically equivalent to the older Heisenberg-Pauli theory.
Equivalent? Really? So the math underneath was the same?
Essentially, yes. Others like Rosenfeld and Dirac-Fock-Podolsky, they confirmed this independently, showed you could mathematically transform one into the other.
Huh. So, same math, just a totally different way of looking at it. Why was that still useful then, if they were equivalent?
That's a really good question. The equivalence was important, sure, but Dirac's theory had this key advantage in interpretation.
How so?
Instead of just asking, where are the particles at this specific moment in time, you can now ask, what's the probability of finding particle 1 at location R1 at its time T1, A and D particle 2 at R2 at its time T2, and so on?
Ah, okay. It lets you ask more complex, time-separated questions that fit relativity better.
Exactly. Bloch discussed this later in 34, really showing the depth of that conceptual shift. It was powerful.
That makes sense. So they had this new relativistic way to think about particles. But what about fields? What happened when they tried to apply this kind of thinking to, say, the electron field, treating electrons as waves?
Right. That was the next big hurdle around 1942, during the war years, which made communication difficult, of course. The problem was still there. The Heisenberg-Pauli field theory used that common time for different points in space.
Which Dirac had already pointed out wasn't really relativistically sound.
Precisely. Yukawa even wrote about this, highlighted the issue, though his own proposed fixes had other problems, like mixing up cause and effect sometimes.
So Tomonaga, remembering Dirac's idea for particles, he thought, why not apply it to points in space?
He did. It sounds pretty wild, right?
Yeah, I mean, if you give each particle its own time, maybe n particles, n times, but each point in space, That's infinite.
It is infinite. That was the bold leap. He bravely assigned a different time variable to each point in space within the field.
And that didn't just explode into an infinitely complicated mess.
Remarkably, no. No essential difficulty popped up because of the infinite variables. He found that a similar interpretation, like Bloch discussed for particles, could work here too. This work started around 42, finished up in 46. It resulted in a completely covariant theory. Relativistically consistent.
And it was still equivalent to Heisenberg-Pauli, just better conceptually.
Exactly. Equivalent, but finally consistent with relativity's demands about space and time. A huge theoretical step.
Okay, so now we have these elegant theories consistent with relativity for both particles and fields. Problem solved. Smooth sailing from here.
Ah, hopefully physics were that easy. No, solving one problem often reveals another deeper one, and this was a big one.
What was it? What emerged next?
Well, now that they had these theories, they started calculating the effects of field reactions. Basically, how a particle interacts with the field it itself creates.
Like an electron interacting with its own electromagnetic field.
Precisely. And when they did these calculations, infinities kept showing up in the answers. It was like a persistent bug they couldn't squash.
Okay, give us an example. Where did these annoying infinities first appear?
The first big one was the electromagnetic mass of the electron. An electron has charge, creates a field. That field pushes back on the electron, changes its effective mass.
And when they calculated that change?
They got infinity. Even classically, Lorentz found this for a point electron. Quantum mechanically, Weisskopf calculated it. Still infinite. A bit weaker infinity mathematically speaking, but infinite nonetheless.
Which is clearly wrong. We measure the electron's mass. It's very finite.
Exactly. So the theory was predicting nonsense. That was the first major headache.
What else went wrong? Were there other places these infinities cropped up?
Oh, yes. The next really critical issue was in scattering processes. Like when an electron bounces off an external electric field.
Okay.
Standard calculations, like the Rutherford formula, they worked perfectly fine if you ignored these field reactions. Matched experiments beautifully.
But you can't really ignore them if you want a complete theory.
Right. So people like Brombeck-Weinman, Pauli Fears, and later Dankoff, they tried to include these reactions. Disaster. Their calculations produced multiple infinities in the scattering results. The scattering cross-section, basically, how likely the scattering is, didn't get a small correction. It became infinitely large.
Infinitely large. Again, totally wrong compared to experiment. This sounds like a real crisis for the theory.
It absolutely was. Deeply discouraging. Many top physicists started losing faith. Some thought maybe the whole idea of field reaction was just wrong, meaningless.
But not everyone gave up.
No. Heisenberg, for instance, he believed these reactions were crucial, not meaningless. And Tomonaga, influenced by Heisenberg, felt this needed a direct assault, a frontal attack, as he put it.
So what did he do?
He started digging into the relationship between these different infinities, the infinite mass, the infinite scattering. He wondered maybe the scattering infinities were just, downstream effects of the infinite mass.
Like symptoms of the same underlying disease.
Exactly. His initial work, using some simplified models, suggested maybe the strongest infinite terms in scattering looked mathematically similar to the mass term.
Okay, a glimmer of hope.
A glimmer. But then Dankoff did a proper relativistic calculation, and he found that, well, part of the scattering infinity still seemed just as bad as the mass infinity. It wasn't all just the mass effect. That was worrying.
So not a simple connection. Did they find other kinds of reactions causing trouble too?
Yes. Besides this mass type infinity, there was another source. Vacuum polarization.
Vacuum polarization.
That's it. Basically how the vacuum itself, which isn't truly empty in quantum theory, kind of screens the electron's charge. Fleeting particle-antiparticle pairs popping in and out.
And that effect also led to infinite results.
Yes. It modified the apparent charge of the electron, and calculations involving it, as Weisskopf showed, also gave infinities. So infinite mass, infinite charge modification, infinite scattering. It was a mess.
Right. Infinities everywhere. So the problem is clearly identified. How do they try to actually solve it? Was there some clever trick maybe to make the infinities just cancel out?
There was a really elegant, quite bold idea came from Sakata in 1946.
What did he propose?
He suggested introducing a completely new, unknown field. A hypothetical cohesive force field that would also interact with the electron alongside the electromagnetic field.
A new force. What was the point of that?
The brilliant idea was that this new field's interaction would generate its own infinite contribution to the electron's mass, but a negative one.
So the positive infinity from electromagnetism and a negative one from this new field.
Could potentially cancel out perfectly. If you chose the strength, the coupling constant of this new force just right, you could end up with a finite, sensible mass. Payuz in the US actually had a similar idea independently.
That sounds incredibly clever, using one infinity to fight another. Did it work for the scattering infinities too?
That was the million-dollar question. Tomonaga and his team jumped on it. They redid Dankoff's complicated scattering calculations, but this time including Sakata's cohesive field.
Did the scattering infinities cancel too?
Well, they did find negative infinities in the scattering results from the new field, but they didn't completely cancel the positive ones from the electromagnetic field that Dankoff had found.
Oh, so it fixed the mass problem maybe, but not the scattering problem.
It seemed that way, or at least not entirely. And it didn't fix the vacuum polarization infinity either. The cancellation wasn't total. It was a bit disappointing.
So, close, but no cigar. What happened next? Did they keep digging into these calculations?
They did. And while they were wrestling with Dankoff's really tough calculations, Tomonaga's group actually developed a simpler way to do them.
A new method.
Yeah, using something he called covariant contact transformations. It was basically a relativistic version of an older method, and crucially, it let them separate out the mass part from the scattering part much more cleanly right from the start.
Okay, so a clearer calculation method, did that lead anywhere?
It led somewhere huge. Because this new, clearer method, which, by the way, cut down calculation time from months to weeks, it helped them spot an error.
An error in Dankoff's original calculation.
Exactly, a crucial error. And get this, Tomonaga's team admitted they'd made the same mistake initially when they first checked Dankoff's work. It was a single mathematical term that had been overlooked.
Just one term. And that made all the difference.
Absolutely vital. Fixing that single error changed the conclusion about the scattering infinities completely.
So with the correction, what happened to the infinities from the electromagnetic field and Sakata's cohesive field in the scattering process?
They canceled. Completely. The infinities from the two fields wiped each other out perfectly in the scattering calculation.
Wow. Except you mentioned the vacuum polarization one earlier.
Right. That one, related to the charge, was still there. But the other scattering infinities, the ones related to the mass term, they vanished thanks to the cancellation once the calculation was done correctly.
That's incredible. A single mistake hiding such a crucial cancellation.
So what did this mean for the big picture, for understanding where all these infinities came from? It meant that the worst parts, the really strong divergences in scattering, could now be blamed entirely on the modification to the electron's mass. The leftover bits, the actual physical effects of field reaction on the scattering process itself, once you accounted for the mass change, they were finite. No divergence.
Okay, hold on. So all the infinite troubles in scattering boil down to just two things. The infinite shift in mass and that infinite shift in charge from vacuum polarization.
Exactly. That was a huge realization. All the infinities popping up could be traced back to either the modification of the mass or the modification of the charge. There were no other inherent infinities lurking in the theory itself.
That must have been a massive relief. But I'm still a bit stuck. If the calculated mass and charge modifications are infinite, how does that help? We still don't observe infinite mass or charge.
Right, that's the crucial next step. And this is what Tomonaga called the pleasant thing. The theory, even corrected, couldn't calculate the finite values of the mass and charge. It still gave these infinite corrections.
But it's still broken.
Not exactly. Here's the leap. The mass and charge we actually measure in experiments, those are the total modified values. And those measured values are, of course, finite.
Okay.
And the theory, it turns out, only ever deals with these final modified values, the original bare mass and charge, and those infinite corrections. They never appear on their own in the equations you use to predict experimental results.
Ah. So the infinite parts are sort of buried inside quantities we never measured directly.
Precisely, which led to this revolutionary idea. Since the theory is, frankly, incompetent at calculating the mass and charge from first principles, it gives infinity. Let's just take the finite values we measure in the lab and plug those into the theory wherever the mass and charge appear.
So you basically say, okay, theory, you can't calculate this part, but experiment tells us the answer is X. We'll just use X.
Exactly that. It's a practical, almost philosophical workaround. Acknowledge the theory's limitation in calculating these fundamental constants and use the experimentally measured values instead.
And this whole procedure, this substitution, what's it called?
It's called renormalization. Renormalization of mass and charge. It was the key that unlocked QED. It suddenly seemed possible that the theory, despite these inherent infinite parts, could actually give finite, physically meaningful predictions for things like scattering or energy levels.
Wow. And you mentioned Dankoff earlier, the one with the error.
Yeah.
Wasn't he already using that word, renormalization?
He was. The term and some of the ideas were floating around. Dankoff even used the word in his paper, which makes his error even more, well, unfortunate in hindsight.
He hadn't made that mistake.
Right. The whole development of renormalization theory might have happened much faster. The path might have been much clearer. History could have been quite different. It really shows how one subtle point in a complex calculation can change things.
Absolutely. So the conceptual framework is there. Renormalization provides a path forward, a way to handle the infinities. What happened next, especially as the world started opening up after World War II?
Well, around 46 to 48, information started flowing more freely. News eventually reached Tomonaga in Japan that Lewis and Epstein over in the U.S. had independently found Dankoff's mistake, too.
So they reached the same conclusion.
Yes, same conclusion about the cancellation. And meanwhile, Julian Schwinger, another major figure, had also developed his own powerful version of a covariant field theory similar in spirit to Tomonaga's. Things were converging.
But wasn't there also a crucial experiment around this time? Something that really showed these field reactions were real and that renormalization was needed.
Oh, absolutely. This is where theory met reality in a spectacular way. News started to trickle out about the Lamb shift.
The Lamb shift, what was that?
Discovered in 1947 by Willis Lamb and Robert Rutherford, they found a tiny, unexpected difference in the energy levels of the hydrogen atom. Dirac's original theory predicted two levels should have exactly the same energy, but Lamb found they didn't.
A small difference, but one that the existing theory couldn't explain.
Exactly. It was a clear signal that something else was going on, and that something else was widely suspected to be these very field reactions we've been talking about.
And how did Tomonaga first hear about this pivotal experimental result? Through the usual channels, physics journals.
Get this, and Tomonaga mentions this himself, the first detailed information he got wasn't from a formal publication. It was from the popular science column of a weekly American magazine.
No way. A weekly magazine.
Yep. Isn't that amazing? A crucial piece of experimental evidence for one of the most profound theories, arriving via popular science news. It immediately kicked them into high gear. Hans Bethe had already done a quick sort of back-of-the-envelope calculation, non-relativistic, but it suggested the shift was indeed caused by field reactions, gave an infinite result initially, but became finite and roughly correct when he applied mass renormalization.
So the moment they heard about the Lamb shift, Tomonaga's group realized their renormalization approach should be able to calculate it properly.
Precisely. They predicted their method, those covariant contact transformations, would be perfect for doing the full relativistic calculation needed to get the Lamb shift accurately. And they were absolutely right.
And this wasn't just happening in Japan, right? This became a global effort.
Indeed. It was a period of intense activity. In the U.S., Schwinger developed incredibly powerful mathematical techniques to calculate it. Kroll and Lamb did crucial work, as did French and Weisskopf. They all calculated the Lamb shift. And also other effects, like the slight difference between the electron's magnetic moment and what Dirac's theory predicted the anomalous magnetic moment.
And Tomonaga's group calculations matched.
Yes. Their results agreed beautifully with the American calculations. It was a convergence of theory and experiment and different theoretical approaches all pointing to the same answer. And then the work of Feynman, with his diagrams, and Dyson, who showed the equivalence of Feynman's and Schwinger-Tomonaga's approaches and proved renormalization works to any order of approximation. That really cemented QED.
It became this incredibly precise predictive theory.
Astonishingly so. And the ideas of renormalization even spread to other areas like statistical mechanics, solid-state physics. It was a paradigm shift.
And Tomonaga, looking back in his Nobel lecture, summed up his own contribution how?
With typical modesty, he said he felt he only played a tiny partial role in the whole development, though history clearly shows his role was foundational.
What an incredible story. We've gone from these deep philosophical debates between Dirac and Heisenberg through this seemingly impossible barrier of infinities.
Yeah, calculations just spitting out nonsense.
And then arriving at this clever, almost pragmatic solution of renormalization that just worked.
It really is a powerful reminder, isn't it, that sometimes the biggest roadblocks in science, the things that seem utterly broken, can force you into a deeper level of understanding. The whole QED story, it shows how theory, experiment, careful calculation, even correcting mistakes, how it all comes together.
It shows physicists faced with infinite answers didn't just throw up their hands. They found a way to connect their imperfect theories to the finite, measurable world, acknowledging the limits, using experiment.
Exactly. They built a bridge between the math and reality.
So a final thought for you listening? If a fundamental theory of the universe could be made incredibly successful by admitting its limits and incorporating observation in this way,
What other problems, maybe ones that seem completely intractable in science or even in other parts of life, might be waiting for a similar kind of creative solution, one that blends the ideal with the real?
something to ponder. Keep exploring those deep dives, and we'll catch you next time.